And welcome back as we continue our cosmic journey. We are now going to turn our gaze a little bit further away from home as we start looking at other stars within the universe. And let's start this conversation off by looking at the brightness of said stars. Now, the first thing we need to understand when we're talking about the brightness of stars is this idea of luminosity. Perhaps the most important characteristic of any star is its luminosity, or the total amount of energy at all wavelengths that it emits per second. Now, if we remember, the sun, which we just discussed recently, gives out a tremendous amount of energy every second, and the other thing we need to remember is that there are stars that are technically more luminous than that of our own sun. So to make the comparison among stars easy, astronomers express the luminosity of all stars pretty much in terms of the sun's luminosity. So for example, if we look at the luminosity of Sirius, we say it's about 25 times that of the sun. We use the symbol L sun to denote the sun's luminosity. So Sirius would be 25 L sun. The next measurement is apparent brightness. Now, astronomers are careful to distinguish between the luminosity of a star, again, the total energy output, and the amount of energy that happens to actually reach our eyes or a telescope here on Earth. Now, stars emit the same amount of energy every direction in space. Remember, they're a big sphere-ish shape of gas that's illuminating out and it's going in every direction. So, because they're going on in every direction, consequently, only a minuscule fraction of that energy that's radiating out into space given off by a star actually will receive to an observer here on Earth. And it doesn't matter whether they're at an observatory on the surface or it's a satellite that's up in space, it's still only going to be a tiny amount of energy actually reaching us. And we call the amount of a star's energy that reaches a given area each second here on Earth its apparent brightness. Now, if you look at the night sky, you will see a wide range of apparent brightnesses among the stars. Now, most stars, when you look up the night sky, are so dim that you need a telescope to detect them. Now, if all the stars in our night sky had the same luminosity, we could see the difference in their apparent brightnesses to kind of tell us how far away they are. However, not all stars have the same luminosity. This means that if a star looks dim in the night sky, we don't know whether it's dim because it has low luminosity but is close by, or whether it has a high luminosity and it's actually very far away. So if we want to measure the luminosities of stars, we have to first compensate for the dimming effects of distance on light, and in order to do that, we first have to know how far away they are. So distance actually turns out to be one of the most difficult of all astronomical measurements that we have to kind of calculate. So in order to try to tackle this, we need to use the magnitude scale. Now, the process of measuring apparent brightness of stars is called photometry. Astronomical photometry began with Hipparchus around 150 BCE. And what he did is he erected an observatory on the island of Rhodes in the Mediterranean. There he actually prepared a catalog of nearly 1,000 stars that included not only their positions, but also estimates of their apparent brightness. Now, Hipparchus did not have access to his telescope. This is well before, for example, the time of Galileo, or any other instrument that would help aid him in his nighttime observation and really measure apparent brightness accurately. So he simply did the best he could and made estimates with his eyes. Now, he sorted the stars into 6 brightness categories, which he referred to as a magnitude. So he referred to the brightest stars in his catalog as the first magnitudes, whereas those so faint you can barely see as the 6th magnitude star. Now, during the 19th century, astronomers attempted to make this scale much more precise by establishing exactly how much the apparent brightness of a 6th magnitude star differs from that of the 1st magnitude. So what did the difference in magnitudes kind of reveal? Well, measurements show that we receive about 100 times more light from a 1st magnitude star than we did from a 6th magnitude star. Now, based on this measurements, astronomers then defined an accurate magnitude system in which a difference of 5 magnitudes corresponds to a brightness ratio of 100 to 1. In addition, the magnitudes of stars are decimalized. So a star isn't simply just a 2nd magnitude star. It may, for example, have a magnitude of 2.0, 2.1, 2.3, etc. And if two stars differ, let's say by 0.75 magnitudes, that means that they differ by a factor of about 2 brightness. Now, if they are about 2.5 magnitudes apart, well, they differ by a factor of 10. A 4 magnitude star is going to correspond to a difference in brightness of a factor of 40. And so when we start going back and looking at this apparent magnitude, because the faintest magnitudes that can be detected by the unaided eye, binoculars, and large telescopes, we can take a look here at this image to really kind of get an idea of how these might appear. The most important fact to remember is that when we're using magnitude, the system goes backwards. So the smaller the number, or the more negative it becomes, the brighter it is to us here on Earth. And you notice the sun is, of course, the object that's going to be to the farthest left, because the sun is the most prominent object in our sky. It appears during the day, and it pretty much is so bright, we really don't get to see much else. You can see the full moon is the next closest thing from there. From there, we have things such as our planets. So you can see we have Venus, for example, and we have Jupiter and Mars. So again, the larger the magnitude we have, the fainter the object you're observing. So again, the further we go towards this positive, larger direction, the fainter the object is in the night sky. Now, there are other units of brightness to consider. Although the magnitude scale is still used for visual astronomy, it is not at all used in newer branches of the field. For example, in radio astronomy, we don't have an equivalent of the magnitude system. Rather, radio astronomers measure the amount of energy being collected each second by each square meter of a radio telescope. Similarly, most researchers in the field of infrared, X-ray, gamma ray astronomy use energy per area per second rather than magnitudes to express the results of their measurements. Now, astronomers in all fields are very careful to distinguish between the luminosity of the source and the amount of energy that happens to reach here on Earth. Because remember, luminosity is a very important characteristic that tells us a lot about the object in question, whereas the energy that reaches Earth is pretty much just a cosmic accident